Welcome to this session on Introduction to Probability and Risk. This is submodule 1 of 4. In this session, we will explore how probability helps us assess uncertainty, model potential outcomes, and support risk-based decision-making in drilling operations. Let's begin by looking at the key objectives of this module. In this submodule, we will develop a clear understanding of probability as a measure of event likelihood. We will examine how probability ranges from events that are certain to those that are nearly impossible, and how this applies in drilling operations. Next, we will distinguish between sure events, which always occur, and almost sure events, which are highly likely but not guaranteed. We'll also learn how to apply probability rules, both for single events and for multiple events occurring together or separately. Conditional probability will be an important focus as it mirrors real drilling challenges, such as estimating the likelihood of stuck pipe when instability is already present. Finally, we will work through applied probability exercises, linking these concepts to practical drilling risk scenarios. This structured approach will give you both the mathematical framework and practical reasoning skills needed to apply probability thinking in the field. Before diving into formulas, it's essential to recognize that probability underpins how we describe and interpret data distributions. Probability tells us not just what could happen, but how likely each outcome is across a range of possibilities. In drilling engineering, this helps us move beyond single-point estimates and think about the spread of potential outcomes, whether we are predicting pore pressure, circulation losses, or bit wear rates. Probability is simply the likelihood or chance that something will happen. We use it to estimate potential events and to understand the mechanics of complex systems. The key is that probability is always defined between 0 and 1. 0 represents an impossible event, while 1 represents an event that is certain. In practice, probabilities are sometimes expressed as percentages or broad categories, such as low, medium, or high likelihood. The definition is straightforward. Probability provides a structured way to quantify uncertainty. This is essential in drilling engineering, where every stage, from spud to completion, carries uncertainty. With the definition clear, let's explore how probability distinguishes between events that are sure and those that are only almost sure. An important distinction is between a sure event and an almost sure event. If an event is sure, it will always happen. There is no alternative. For example, if every drilled well requires casing, that's a sure event. But an almost sure event is slightly different. A probability of 1 means the event will almost surely occur, but there are still theoretical possibilities for exceptions. For instance, when we say a drilling fluid will almost surely reach bottom hole, there may still be rare circumstances such as a blockage where it does not. This distinction reminds us that even highly probable outcomes can carry residual uncertainty. With that perspective, let's reinforce the basics using a simple exercise with a coin toss. Here, we illustrate probability with the familiar example of tossing a coin. A fair, non-tampered coin has 2 equally likely outcomes, heads or tails. The probability of getting a head is 1 event out of 2 possible outcomes, or 1/2, expressed as 0.5. Now, if we tamper with the coin, say by filing or weighting it, the chance of heads increases above 0.5, but we can't assign a precise value without testing. At the extreme, if both sides of the coin show heads, then the probability becomes 1, a certainty. This simple example demonstrates how probabilities change with altered conditions, a principle that directly applies in drilling risk analysis. For instance, if formation instability increases, the likelihood of stuck pipe shifts from a low to a much higher probability. Next, let's formalize this with the mathematical treatment of single events. The probability of a single event A occurring is written as P of A, and it must always lie between 0 and 1. For example, if the probability of a kick is 0.2, that means in the long run we expect kicks in about 20% of comparable wells. The probability of event A not occurring is equally important, and is defined as 1 minus P of A. So if the chance of a kick is 0.2, then the chance of no kick is 0.8. This simple complement rule ensures probabilities always balance to 1. These definitions form the backbone of probability analysis. With single events clear, we can extend the logic to multiple events happening together or separately. When working with two independent events, A and B, the probability of both happening together is found by multiplying their individual probabilities. This is written as P of A and B equals P of A times P of B. For mutually exclusive events, where only one can occur, such as rolling either a 5 or 6 on a die, we add the probabilities together. That is, P of A or B equals P of A plus P of B. If the events are not mutually exclusive, meaning they can occur together, we adjust by subtracting the overlap, P of A and B. These rules are essential when modelling drilling risks, such as the probability of lost circulation combined with stuck pipe, or multiple hazards occurring simultaneously. To see how this works in practice, let's look at an example with dice. Consider rolling a 6-sided die. The probability of rolling a single one is 1 out of 6. If we roll 2 dice and want both to land on one, we multiply. 1/6 times 1/6, giving 1 over 36. That's a low probability, but not impossible. Now if instead we want to know the chance of rolling either a 5 or a 6 in a single throw, these are mutually exclusive outcomes. We simply add 1/6 plus 1/6, which equals 1/3. These exercises show how probabilities combine in different scenarios. In drilling, we often evaluate whether risks are independent, mutually exclusive, or overlapping before applying these same rules. The next step is to look at conditional probability, where one event depends on another. Conditional probability looks at the likelihood of one event occurring given that another has already happened. A classic drilling example is the probability of stuck pipe given the occurrence of wellbore instability. We write this as P of A given B. The formula is P of A and B divided by P of B. If the probability of the condition B is 0, then P of A given B is undefined. It makes no sense to condition on something impossible. This relationship is also formalized in Bayes' theorem, which lets us update probabilities as new evidence emerges. In drilling, Bayes' logic helps when we receive new data, such as mud logging or LWD readings, and must adjust our risk estimates accordingly. To test this idea, let's walk through a real-world style exercise. Here's the setup. In a school, 60% of students are boys and 40% are girls. Girls are equally split between wearing trousers and skirts, while all the boys wear trousers. Now imagine an observer sees only a student wearing trousers. What's the probability this student is a girl? This exercise challenges us to use conditional probability. First, we must calculate the overall probability of any student wearing trousers. Then, using Bayes' approach, we find the conditional probability that the trouser wearer is a girl. It's a direct analogy to drilling, where we often start with general risk estimates, then refine them once we observe specific conditions. On the next slide, we'll review the worked solution. Let's solve it. The probability of a student being a girl is 0.4, while for a boy it's 0.6. The chance of a girl wearing trousers is 0.5, while for a boy it's 1.0. So the overall probability of seeing trousers is 0.5 times 0.4 plus 1.0 times 0.6, which equals 0.8. Now, to find the probability that the trouser wearer is a girl, we multiply 0.5 by 0.8, 0.4, then divide by 0.8. That equals 0.25 or 25%. This confirms that, although the observer only sees trousers, the likelihood of the student being female is just 1 in 4. It's a strong illustration of how conditional probability adjusts our expectations when we introduce new information. With this practical example in mind, let's revisit our learning objectives. Let's reflect on what we set out to learn. First, we defined probability as a measure of event likelihood and demonstrated its use in describing uncertainty. We then differentiated between sure events and almost sure events, highlighting the subtle but important distinction. Next, we applied the core probability rules for single and multiple events, using examples like coin tosses and dice rolls. We advanced into conditional probability, where we linked real drilling risks to mathematical treatment, and finally worked through exercises that tested practical application of these principles. Each objective, understanding probability, differentiating event types, applying rules, calculating conditionals, and interpreting risk exercises, has been addressed with both definitions and examples. With this review complete, let's formally close the submodule. That concludes this submodule 1 of 4 on Introduction to Probability and Risk. Please proceed to the quiz to check your understanding of the material. Thank you for your attention, and I look forward to continuing with you in the next submodule.